Great. Hello everyone, welcome to Tuesday. I'm delighted to introduce Niamh, who's going to tell us about decomposition matrices for quasi-isolated blocks of exceptional groups.
Thanks very much. Yeah, welcome to Tuesday indeed. So first of all, thank you to the organisers for inviting me to be here and also for this opportunity to speak. So a little different format to my normal talks, I think most people's normal talks. I'm giving this talk while I'm in the middle of a problem rather than while I've finished a problem. So this is more a presentation of issues than a presentation of solutions, but maybe this is the right audience to present this kind of thing, who knows? Who can help? So decomposition matrices for quasi-isolated blocks of exceptional groups. I'm going to split the talk in two parts. In the first part, I will talk about decomposition matrices in general. And then in the second half, I want to talk specifically about finite groups of Lie type. What are quasi-isolated blocks? Why are we looking at them? And how we might hope to tackle this problem. So, start at the beginning with an introduction. Okay, so throughout, G will be a finite group. L will be a prime number. And I will assume that L divides the order of the group. Okay, so what we're interested in here is the modular representation theory of this finite group. And the decomposition matrix is a way to numerically connect the representation theory over characteristic 0 and then the modular representation theory that we're interested in. So it is a fundamental part of studying modular representation theory because generally we know things about characteristic 0 and we don't know anything about characteristic L, and the decomposition matrix sits in the middle and tells us the relationship between the two. So in order to do this, we want to work over what's called an L modular system. So I will denote this by KOK. So this is an L modular system for G, and this gives us a mechanism to go between characteristic 0 and characteristic L. So what are these things? Well, O is a complete discrete valuation ring, and I will denote its maximal ideal by M. Okay, now we want the characteristic 0 stuff, so that will be this capital K, which is the fraction field of our valuation ring. So this is a field of characteristic 0. And then on the other side we have this little k, which is the residue field of O over its maximal ideal. So this is a field then of characteristic L, and we're going to assume, as I said, that L divides the order of the group, so that this thing is not semi-simple. Okay. So I'm going to define decomposition matrices in a purely character theoretic manner. Obviously there's all of the modules sitting behind this. So what do we have? We have three group algebras. So we've been embedding it this way, and we would surjection out that way. And with this system in place, we now have two different character theories. So the first character theory, I will denote the ordinary irreducible characters of G by ear of G. Okay, so these are the characters here for representations over this field of characteristic 0, so you can just think of these as the normal complex valued characters. It will be the same character theory even if you just think over C. Okay, but we also have a character theory on this side, and I'll denote those irreducible characters by IBR of G. So these are irreducible Brouwer characters of G. Okay, I'm not going to define what these are explicitly, but let me just say they're defined they're not characters, so you can't define a character for any element of G if it's a Brauer character, but it's only for elements of what I will denote by G0, and this is the set of L regular elements of G. So elements G and G, such that L does not divide the order of G. Okay, so we have these characters and they're defined on G0. What do we do? Unfortunately, you can't just take the trace of a matrix if you're working in a field of characteristic L. If you just took the trace of a matrix, then for example, you'd only get the degree modulo L. So you lose too much information. And so what you have to do is take the eigenvalues of that matrix. These will be L prime roots of unity, and you somehow lift them to a field of characteristic 0, and in that way you can add them up there and you don't lose any information. Okay, so you do this in a coherent way, so it's not quite the same, but the two theories are essentially analogous character theories. Okay, so we now want a connection between these two character theories. So if we start out with chi, an ordinary irreducible character, I want to denote by chi 0 is just a restriction of chi to this set of L regular elements of G. And the important fact here is that chi 0 is a Brauer character of G. Okay, and as in the ordinary character case, the Brauer characters form a basis for the class functions now on the L regular elements. And so you can express this chi 0 as a linear combination of some non-negative integers, which I'll denote by d chi phi, times phi, where phi now runs over the irreducible Brauer characters of G. So this is for some d chi phi in Z greater than or equal to 0. Okay, and this is exactly the connection that we're interested in. So we're interested in how many times does an irreducible Brauer character phi appear in the restriction of an irreducible ordinary character chi. And we'll put all of these numbers in a matrix, and this gives us the decomposition matrix. I'll denote it by dec of G. And it's just a matrix of all of these non-negative integers d chi phi, where chi runs over ordinary irreducible characters and phi runs over irreducible Brauer characters. Okay, I guess pretty obviously these things here are called the decomposition numbers. Okay, so this is what we're trying to calculate. In my situation, I'm trying to calculate this for quasi-isolated blocks of exceptional groups. But before we get into what that means, I just have one or 2 points on how you can tackle this problem in general. So one way would be if you knew both character tables. Well, if you knew both character tables, you don't need to calculate the decomposition matrix, you know everything. But you might think you know things in characteristic 0, and you might be able to play around with figuring out these numbers. But there's a whole other way to look at this. Well, a whole other way, the opposite direction. So if you have, so this is called Brauer reciprocity. Brauer reciprocity. So it's an alternative viewpoint on these decomposition matrices. So we looked at our matrix, we took a chi, and what we calculated with chi 0 is the sum here across a row. So we took d chi phi and we let phi run over IBR of G, and this was the restriction of chi to the L regular elements. Okay, so if you could calculate those things, well, great. What if you can't? One other way to think about this is to start with the phi and consider what is the column going with that phi. And so if you take the sum here, So now we're summing over all of the characters chi that appear in this column. And this will be denoted by capital phi, small phi, so phi. It'll come up again, so getting used to it. So phi is in fact the character of a projective, indecomposable, capital KG module. And it's the projective indecomposable, so you start out with the simple module corresponding to your Brouwer character in little kg. You take its projective cover there, you lift it to O, you tensor by capital K, and then you get the character of a projective indecomposable KG module. So these are called PIMs. So this is an alternate way to look at these matrices. If you knew all of the PIMs in capital KG, and if you knew the character of each of your PIMs, then you would also be done. So, two different routes to the same problem. Okay, one simplification that you can make, and that we do make, is that we can look instead of the entire decomposition matrix altogether, you can just look at the bits of the decomposition matrix on blocks. So I'll give a quick reminder of what that looks like. So if you take the identity element of your middle group algebra OG, and you split it into a unique sum of central, primitive, idempotents. That then gives you a decomposition of the group algebra, so OG then splits into OGB1 to OGBR. Okay. And each of these things is a minimal two-sided ideal. It's what I will call a block of G, or it could be an L block of G if you want to be specific about the prime that you're using for your modular system. Okay. So we have a way of splitting up this group algebra in the middle, and you're thinking decomposition matrix connects the character theories on both sides of this group algebra. So we need a way to connect the character theories now with the blocks. And so if I let BI just be the block OG BI, I can define ordinary characters in blocks, and I can define modular characters in blocks. So what do I say? I say that the set of ordinary characters in this block is any chi such that if I take this block idempotent BI and I multiply it by E chi, this should be non-zero. What is E chi? It's the central primitive idempotent of capital KG associated to chi. Okay, so any ordinary irreducible character chi, you can define an E chi. I could give you an explicit formula, but it's not very interesting, so I won't bother. And so if that central primitive idempotent times this block idempotent is non-zero, then you say that that character is in this block. Okay, we also need to know what the Brouwer characters in a block are. So this is all the phi in IVRG. And now we need to take the image of this block idempotent in little kg, so we need to quotient it, mod L. We want to multiply it by the simple module affording this character. And we say that the character is in the block if that doesn't kill this module. So this is the simple little kg module associated to our irreducible character phi. Okay, and then I'll just write it here. So with this you get a partition of the ordinary irreducible characters of G into blocks. And similarly, Same thing for IBR of G. Okay, what use is this? Right, we've talked about blocks and we've talked about characters and blocks. The important thing here, in connection to decomposition matrices, is that if d chi phi is greater than 0, then chi and phi are in the same block. And so that means that of G splits into block diagonal form. How many did I say? Yeah, they are. And so you can calculate decomposition matrix of G block by block. And this is, when you get into a difficult problem that you can't do, this is at least one step that might help. Because maybe you can do it for a block when you can't do it for the whole group. And indeed, this is how this problem is usually tackled. So I want to give one very tiny example before I move on to finite groups of Leibniz, just to show what happens. Okay, my group is really S3, and L is equal to 2. So the ordinary irreducible characters, there's just 3 of them. The trivial character, the sign character, and something I'll call chi. There's only 2 Brouwer characters. Trivial character and phi, let's say. So how do the blocks work in this situation? It turns out there are 2 blocks. There's a principal block, and then there's a block of character defect 0. Decomposition matrix then. I just wanted to. So you get. One. Okay, so this is how the decomposition matrix looks. And so you can clearly see that there are 2 blocks here. And so in the first block you have 2 ordinary irreducible characters and 1 Brouwer character. And in the second block you just have 1 of each. Okay. Sadly, things are not quite so easy in the finite groups of Leibniz. Also, as n gets slightly larger. Okay. So section 2 then. What do we do for finite groups of B type? Okay, first of all, I need to give you some basic notation before I can go any further. So we let G underline be a connected reductive algebraic group. And it should be defined over Fp bar, where P is a prime not equal to L. So the situation I'm interested in is this non-defining characteristic. I'll take F to be a Frobenius isomorphism with respect to an FQ structure where Q is some power of P. I want to let G star underline and F be dual to G underline and F. So this is to do with, you start out with your algebraic group with a root system. It's got co-roots, or roots and co-roots, and if you flip the roots and the co-roots, you get a dual group G star. So for example, in GLN the dual group is itself, or in SLN you get PGLN, or PSLN rather. Okay, so what is the group I'm actually interested in? This is an algebraic group, but I want to study the finite group of fixed points. I'll just denote it by G. and I'll denote G star for the fixed points of the dual group. Okay, so these guys are finite groups of Lie types. Okay, and straight away I'm going to make some assumptions to make my life easier. So this is partially just so that I can write down the theory without having to write down lots of different situations. Also because a lot of the stuff doesn't work without these assumptions. So I'm going to assume that the center of G is connected. And I'm going to assume that L is good for G. So just think L is relatively large. If you want to be safe, let it be greater than or equal to 7. Okay. So we're trying to determine decomposition matrices for this group here. And the first thing that we need to do before we start is find some parametrization of the blocks so that we can split our decomposition matrix up and we don't have to do the whole thing at the same time. Okay, so we're going to think about characters and how we can split characters into something parametrized, and we find that there is a partition of the ordinary irreducible characters into what are called Lustig series, which I won't define formally, but these run over the conjugacy classes for S a semi-simple element of the fixed points of the dual group. Okay, so for every conjugacy class, we get a bunch of ordinary irreducible characters. And now we want some way to connect this back to the block partition that we had before. So we said that ordinary irreducible characters are partitioned across blocks. So does this work with that? Luckily it does. So by results of Roy and Michel, you can take a union of these Lustig series. I'll denote it, so let S be L prime first of all. Then, so instead of E of GS, I'm now going to denote by E sub L of GS. It's a union over all the L elements, all of the T's, in CG star of S L. So L elements in here, and I'm going to take the union of these Lustig series. Now, why am I doing this? The point is that this is a union of blocks. So I said earlier we can split things into blocks and calculate decomposition matrices for each block. In this situation, what we're actually going to do is try and calculate the decomposition matrix for the union of blocks corresponding to this S. So dec GS then is this block matrix where each of these BI's is an element of ELGS. So each of these BI's is in this union of blocks. Okay, and this makes sense because this is the way the theory works. Okay, so what do we know already about decomposition matrices here? Maybe a dangerous thing to write down when the first thing I'm going to say is I'm not going to tell you everything that's known because I will undoubtedly leave something out. There are loads of separate independent results in this area, different types of groups, different types of S, very particular things. I'm just going to give a quick summary of some of the things. If L divides Q minus 1, then the decomposition matrices can be calculated by results of Puch. Okay, this already tells you, or gives you an indication that it is expected that these decomposition matrices don't depend on L or Q independently, but only on their relationship. Okay? And that is certainly true when L divides Q minus 1. So that's one case that we won't be looking at, so I will assume, therefore, that L does not divide Q minus 1. Okay. Another situation where everything almost is known is where you have cyclic defect groups. And this is a more, I mean, the Puch result is old. This is still not out, as far as I know. So Craven and Pessar are looking at the Brouwer trees for all of these situations, and so from there they can get the decomposition matrices. Okay, and what else? Most other cases that are known are specific situations where S is equal to 1. And these are what are called unipotent blocks. And really when I say most of what is known, so either just the unipotent situation is known, or the general situation is known because there's a reduction to the unipotent case. So this is really, most of everything is unipotent. Emphasize it, and even still, this is a hard problem. And I'll give you an example as to why. So if G is equal to S, what do we want? SU3 of Q squared, and L is greater than or equal to 5, so L is large, essentially, and B is the principal block. In theory, the block that, okay, it's the biggest block, so it's the most difficult one, but at the same time we know a lot about it. Turns out the decomposition matrix, so dec G of 1, the unipotent of this specific block, maybe I should say, that E, looks like this. Right? Pretty small. But this alpha, okay, it's equal to 2, we know it now, but it was only proved in 2002. By Okuyama and Waki in 2002. So, it's pretty astonishing, I guess, that this small example was still not known in its entirety until 2002. So, this is indeed a difficult problem.
How can the decomposition matrix be squared?
So this is only the bit of the decomposition matrix with the basic set, which in these situations is all you need to calculate. You can calculate all the underneath bit. So in a unipotent, in a unipotent block, you have a unipotent basic set. So this is just the decomposition of the unipotent characters.
Thank you.
So this is really all I'll ever look at also. Fair point. I'll ignore the rest. Okay, I may as well just write it up. When S is not equal to 1, almost nothing is known. Which is where the reduction of Bonifay.Ruquier comes in, which tells us we don't need to do everything. So this is Bonifay.Ruquier in 2017, when they say that if you can take L star, the minimal levy of G star containing the centralizer in G star of S, then So the union of blocks which we're interested in, which is EL of GS, so we're looking at blocks of G in this series S, that's what we want to know about. These blocks are Morita equivalent then to EL of LS. So you've reduced from your group G to your group L, and you're looking now at blocks of L in the series S. So this means that we have a reduction to what are called quasi-isolated blocks. And so these are the blocks ELGS, where you can't find such an L star. So if you can find an L star containing the centralizer, then you can reduce to that Leibniz group, which is smaller. If you can't find an L star, so if the centralizer in G star of S is so big that there's no levy between that centralizer and the whole group, then you call S quasi-isolated, and you call the blocks quasi-isolated. So this is where there does not exist a proper levy L star containing the centralizer in G star of S.
You can give an example of that.
These are classified. So if you go, for example, in F4, there's an element of order 2, and it's centralizer. I mean, there's a list. Yeah, so that's the, yeah.
So this is maximal class groups. So not maximal, not class, maximal rank.
Maximal rank groups. Yeah, I guess their centralizers are of maximal rank. Yeah. Yeah. Right, so these things, this is a massive reduction, right? You've gone from needing to do decomposition matrices for every S to just needing to do these quasi-isolated S. And these, Bonifay has written a list of all of these quasi-isolated elements. So now you can just go through them one by one. Okay, finite list sounds easy. So what is the aim of what I'm trying to do? On the back of this result, I guess, is I'm looking at the case where G is exceptional. I still have the assumptions from before that the center is connected, they're gone. Center is connected, L is good. And now I'm assuming that my S is an L prime semi-simple quasi-isolated element. Okay, and then we want to determine depth of GS. So this matrix up here for all of the blocks in the union of blocks corresponding to S. Okay. So I've already told you it's a hard problem, and that we don't know very much about these blocks. We really only know stuff about unipotent, so what is the general strategy here? And why can we hope to do something now on this, when we didn't hope to do it before, necessarily? So the general method I'm using is to adapt ad hoc methods used for unipotent blocks to quasi-isolated blocks. And what makes us think this might be possible would be that we have what's called a Jordan decomposition. So this takes us, gives a bijection on the ordinary characters in this Lustig series corresponding to S. To the unipotent characters of this large centralizer CG star of S. Okay, so this in its most basic form, that's all you have, is a bijection between the ordinary characters, which at least gives you a labeling for that basic set we discussed, mentioned earlier. So this will in fact be a basic set, because I've made nice assumptions. This is going to be a basic set for the decomposition matrices that I'm trying to calculate, and at least it gives me a labeling for those characters. So it's a starting point. And in fact, it's conjectured that this comes from a Morita equivalence up to reordering of rows and columns, you would then expect that the decomposition matrix of this side that we're interested in is just equal to the decomposition matrix of the unipotent blocks of the centralizer. So there's lots of people that have stated this conjecture, but that is essentially the hope or the aim, the end goal, I guess, is that we expect that to be true. We have no idea how to prove it, but that's where we're starting. So the strategy that I'm using then is to say, well, how did these decomposition matrices on the right-hand side get calculated? Are they known, first of all? Because we're assuming that G is exceptional, I'm going to write mostly, okay, in E8 there are some situations where this is not true. This C, G star, of S is a small rank, or a product of small rank, classical groups. Okay, why is that important? Well, we have results of Duda-Mala. I think the first one was 2014, and the most recent one was last month. So there's a series of papers where they calculate many unipotent decomposition matrices for small rank classical groups, and now some exceptional in the latest one. Let's just say small rank groups. Okay, so in general, I mean, I'm starting with the case of F4, and so these centralizers really are very small classical groups, and so these decomposition matrices are known, and so we have an expectation of what I'm supposed to find on the left-hand side, first of all. And then we also know some methods that they used on the right-hand side, which hopefully, even though Jordan decomposition is just a bijection, you hope that in some nice situations you get more than that, and so you can use stronger machinery. Okay, so I wanted to give two examples of, so far, where I have managed to transfer some of the methods. This is really only the beginning of the story, I suspect. So the other thing about this Duda-Mala papers is that certainly in the last one they give a very nice comprehensive list of all the methods they've used. And so you can literally go through and say, can I transfer that one, can I transfer that one? And it's a practical way to do this. So this is the inductive or computational argument. So on the unipotent side, you would usually expect to know the decomposition matrix of a levy, because it's smaller, and you know things in unipotent. So on the non-unipotent side, you already don't know necessarily the decomposition matrix of a levy. If you're in F4 and you have a type B levy, and it's a non-unipotent block, you're already not sure what's going on down there. So inductive arguments aren't obvious in the same way that they might be easier, certainly, on the unipotent side. But if you're in this situation, so it's a very particular situation, so you take your G star, if you have a one-split levy, L star, which contains your S, don't go away. So if you can find a one-split levy containing S, such that C L star of S is a levy of L star. So this is the very nice situation, and then a result of Bonnefier-Ruquier.
Sorry, what does one split mean?
One split on the spot. What does one split mean? It's the centralizer of phi 1 torus. So we have a result of Bonnefier-Ruquier, which is like a weaker version of their main reduction, which was from 2003. And that tells us that the decomposition matrix of this levy now, so of the dual of this L star in series S, is equal to the decomposition matrix of C L star of S 1. So the unipotent decomposition matrix of this centralizer. So this doesn't work in all situations. You really have to be careful, and it certainly doesn't work at the G star level because we started out with a quasi-isolated S. So you have to go down a level and see if there is a situation where you can find a centralizer in a one-split levy, which is a levy. Then you have this, and we're going to assume that this is known. And certainly for F4, these are now all known. All of the possible situations down here would be known. Okay, so that means we know this decomposition matrix of the levy. And now we can apply the usual inductive arguments that are used in Duhamel and elsewhere, I think. So if you take phi phi, a column of this known decomposition matrix, because it was one split, this is where you need the one split, you'll know that RLG, so the Harris-Chandra induction, this is just a sum of ordinary characters. So now you're doing Harris-Chandra induction of this sum of ordinary characters, and this is a sum of columns of the matrix we're trying to calculate, dec G of S. So you have a projective indecomposable character phi phi for your levy. You induce it to G, and you don't get a projective indecomposable character, unfortunately. You get possibly a sum of projective characters. So all you know now is you have a sum of columns. So somehow you have to decompose this into indecomposables. Okay, and this is not always possible or obvious how you would do this. One thing that you could use is just the block distribution of the characters. So you now have a list, this is a list of ordinary irreducible characters of G. If you know that they're in different blocks, well then the projective has to be two different columns because they can't overlap. The other thing that you can do is guess at what the decomposition might be, or systematically work through all of the possible decompositions, if you have the time. And then any decomposition you might restrict the new things you found, and if they don't give you projectives in the levy, then they can't have been projectives upstairs. So this is a rather laborious process, even in F4, where things are tiny. But it does, in some situations, give you everything you need. So, for example, if G is F4 of Q, and if your centralizer CG star of F is of type A2, then if L divides Q plus 1, you have 4 blocks. And so this block distribution step is fairly, gives you a lot of information. You still do need to do the restriction stuff though. If L divides Q squared plus Q plus 1, then there's only one block, so this first step doesn't do anything. And you only have this restriction argument that's possible. But in both of these situations, you can then figure out the entire decomposition matrix. And indeed, it is the same as the one you were expecting on the other side, just as well, because that would be quite a shock. So, this is the first method that I tried to apply. And as I say, it works in some situations. In other situations, though, you just get a few columns. And you know the size of the matrix you're looking for, and you might know now you have 3 columns. Well, that's not really any use to anybody. So, I then tried to move on and find something a bit more theoretical, let's say. The other thing to mention here, and I should have maybe mentioned it before, is that we have a result by Bruna, Duda, Taylor from 2019, which says that unipotent, under some conditions on L and Q, unipotent decomposition matrices are unitriangular. And I know that Duda and Mala were assuming this even before that had come out, because it was on its way. And so when you're doing this ad hoc restriction checking, is it a projective, how does it work, how does it decompose, this unitriangularity would be really helpful. Sadly, we don't know this to be true in the non-unipotent case. So even though we know that, well, we expect that we're going to get the same matrices, we cannot use that logic yet, until some people expand their results. So this is a real There are more situations on the unipotent side where you might be able to get full matrices using this inductive argument that you can't on the non-unipotent side. Okay, in the last couple of minutes, I'm going to state something extremely vague. So the second method that I have tried to adapt, well, it's not even really adapting, it's just apply directly in a way, is using Hecke algebras. So I'm going to state it as a proposition because I don't want to define anything. It's too late, we don't have enough time. So, if you suppose that CG star of S is of type A and is not twisted. I'm hoping I can remove this non-twisted, but for the moment it should stay in. And then suppose that you have a column phi phi on the unipotent side. So the column of the decomposition matrix of the centralizer unipotent blocks. And suppose that this is labeled, right, we're in type A, so we know that all of these columns will be labeled by partitions. So if it's labeled by L regular partitions, okay, this is a result of, I guess it comes from Dipper, but James wrote it down where he calculated all of the decomposition matrices for GLN up to n equals 10. So he says in there that if you look only at the L regular, the columns labeled by L regular partitions, then they are going to be determined by a Hecke algebra. And the claim of this proposition is that this column, phi phi, is also a column, like a full column, of the decomposition matrix that I'm interested in, so the quasi-isolated blocks of G corresponding to S. And, okay, in 1 second, why does this got anything to do with Hecke algebras? So as I said, this phi phi is determined by the decomposition matrix of a particular Hecke algebra. Let's call it H, and the point here is that you can show that you can analogously define one on the other side, so that the analogous Hecke algebra on the non-unipotent side is the same. Okay, why is this enough? You know, so on both sides you have this result which says the Hecke algebras will determine something in the decomposition matrix. That is not unipotent specific. What is type A unipotent specific is that you'll get a full column. And so if you didn't know that, well then you'd know that you had some entries of a column somewhere in your matrix, and this wouldn't exactly be enough. So in this situation, when you're really looking at type A, you know you get a full column, and so you must, because the decomposition matrices are the same size on both sides, you know that you must also get a full column on the quasi-isolated side. And I think that's probably a good place to stop.
Any questions or comments?
What's the decomposition matrix of the Hecke algebra?
Of the Hecke algebra. So it's an algebra over OG, and then you can consider multiplicities of simples in characteristic L appearing in restrictions of your characteristic Z stuff. So it's essentially the same thing, except you're looking at a Hecke algebra instead of a group algebra. It's like, you could call the decomposition matrix of G the decomposition matrix of OG, right? So it's the algebra that you're really looking at, and you're taking this, so you have a similar system.
do for G2?
For G2 is done.
That's easy, right?
Easy. Someone did it. His has done it, I believe, or at least His did bits of it and someone else did other bits of it. I mean, as far, yeah, so I'm not looking at G2, I'm F4, E6, E7, E8.
Is it a parcel?
E6, I mean, I'm going to look at the adjoint type, I'm not going to bother with centers for the moment. I mean, there's so many obstacles in this that really you have to restrict what you're looking at. And even deciding which bit to focus on was my biggest problem so far. So that's why I'm looking at this stuff with the centralizer of type A. But this result then would apply to all of them, right? If the centralizer is of type A, non-twisted, this Heck algebra stuff should work. And the next step then is to look at the Q-short algebra, which is like a beefed up version of the Heck algebras. And in type A, that should give you the full decomposition matrix. So then, if I can do that, hopefully in May, I will be telling you that we know that if your centralizer is of type A, and it is determined by Q-short algebra, then you get the whole thing. And that would be for any F4, E6, it would be for all of them. Yeah, so it would be general.
All right, let's thank Niamh again for having us talk. We will meet at 10 past, so just under 15 minutes time at the Universität to go to lecture.